Hey, welcome back to Math with Patrick and Quill. Today is November 4th, and we're talking about problem 308 from the Daily Epsilon calendar. And I say talking about because this honestly goes way above my head. These are like PhD topics, in my opinion, of topology, differential geometry, like calculus, I don't know, very difficult concepts. I only have a very surface level understanding of this that I'll try to share with you. And hey, if you know more than me, then that's totally fine. This is as much as I can share with this problem today. So let's try to work through it together. We are finding the only x. I'm stopping there because I want to talk about what this x is doing down here with this kind of double bold r. So if you imagine doing something to the power of 1, that's like the same thing as doing like nothing. And so r1 would just be r, and this is the symbol that we use for the real numbers. And so if x is 1 today, we're talking about the real number line, essentially just a one-dimensional line that goes to both of the infinities in either direction. Once we stick a 2 on it, this is just the real numbers but going in 2 dimensions. And so now this is talking about basically the entire real plane. And then once we talk about R4, this is talking about, R3, this is talking about basically all of just Cartesian 3D space. This symbol R3 here to me is representing just what 3D space is. And then R4 is now talking about four-dimensional space. Apparently that has to do with our answer today, and I guess we'll kind of get to that or cross that bridge once we get to it. Just because for me it's really hard to visualize this problem in 3 dimensions and then 4 dimensions, I'm really only going to stick with 1 and 2-dimensional objects. And those objects that we're talking about are these differentiable manifolds. I just learned a few days ago that a manifold in math is essentially just a thing that on the kind of small scale, so here's my thing, it's going to be like this curve right now. And on the small scale, if you zoom in, it looks like just a line, just like essentially, it looks like a real number line. And so this kind of curve, this squiggle that I drew, essentially just a thing, this is considered a manifold because on the small scale, this behaves similarly to one of these r's with maybe an exponent on it. And so maybe a two-dimensional manifold could be, say, just a surface like this. Maybe I'll put in some grid lines just to show that it's kind of being warped in certain spots. But since this is on a small scale, right, if we like kind of zoom in to just a small picture, this is basically just doing what a normal plane would do. Then this is not only is it a manifold, but it is homeomorphic to our like r squared or r2. I might be saying that wrong. I actually don't know the right way to talk about these superscripts. I'm just going to keep calling it R1 and R2, maybe R3 if I want to talk about the third dimension there. So backing up, a manifold, again, is just kind of a thing that behaves similarly on a small scale to lines or planes or 3D space. Again, that's hard for me to conceptualize. Real quick, a circle is also going to be a manifold. This would technically be I think a one-dimensional manifold, again, because when we zoom in on a certain part of it, it behaves like a line or a one-dimensional object. A sphere, then, even though it's like a 3D object, I think this would be considered a 2D manifold because a little patch of a sphere acts the same way as a plane would. And when we're talking about a differentiable manifold, this just means that essentially everywhere it's smooth. So like a sphere is going to be a differentiable manifold because everywhere it's pretty smooth. Maybe something that isn't would be something that has like a crease in it. So we could like puncture a little hole and then, I don't know, the rest of it could kind of look like this. So maybe a little bean shape kind of thing would not be a differentiable manifold, specifically because we have some kind of crease or edge happening there. Differentiable, kind of from calculus, just essentially means smooth, and so we can't have any kinks, we can't have any holes. Actually, I think we could have holes in it and have it still be differentiable, but we definitely can't have any kinks like this. And so that's what it means to be a differentiable manifold, essentially something that behaves like a line or a plane, or maybe 3D space, but maybe we're warping it a little bit. But we're not warping it too much such that we have any creases, edges, or corners. All right, and I did touch on the word homeomorphic. This is basically like kind of the same or like geometrically the same. Maybe you've heard that kind of topology joke that topologists consider mugs and donuts to be the same thing. That's just because both of these objects only have one hole or kind of puncture here. I know that this mug is vacant here, but maybe you could imagine like a thicker mug, kind of like this. Say this is like the cross section right here. And here's a little handle loopy. And if I kind of nudge this base a little bit higher and higher and higher, basically I could just fill in all of this as a sphere. And topologically, I'm not fundamentally changing its shape. I'm not including more punctures. I'm not adding any folds or creases in it. Basically, we still just have this like one hole, as does this donut right here. And so that's kind of what it means to have a homeomorphism, or for two objects to be homeomorphic, is that they have the same general shape, but we can like warp one to become the other. Also, I think I just remembered, so if we have a crease, say in a plane like this, these two things I think are still going to be homeomorphic to each other. I hope this is the right symbol. Again, I'm not too educated on this. The kind of creased plane is still going to be homeomorphic to the plane itself. So a homeomorphism doesn't really care or mind about these creases or edges, because we could still kind of fold this part down flat, and then we would still get a plane. One thing that does matter, though, and let's actually talk about that creased plane example again. This diffeomorphic idea means that we can go between two objects without creating or encountering any creases. The prefix like diffeo refers back to like derivative or differential from calculus, I think, where anything that's differentiable is smooth. This is a one-dimensional manifold that is a differentiable manifold because it's smooth everywhere. We don't have any creases or kinks anywhere. And a diffeomorphic process to go between two shapes just can't encounter any of these harsh edges. And I think that about cuts it for vocabulary. And so let's see what we can do in R1. Basically, I'm going to just do my little guess and check strategy here and see what happens when we think about x with small numbers. Okay, so let's imagine we're in just R1. We're only thinking of one-dimensional objects, so lines or curves, maybe closed curves as well. So this circle is technically a one-dimensional object for me. We're trying to find a differentiable manifold. So here, let me draw a few examples of differentiable manifolds. We could have squiggles, we could have circles, we could have lines, just things that we can't have right now, or things with creases in it. So hopefully one of these differentiable manifolds, and we're seeing if it's homeomorphic, but not diffeomorphic to R1, as in it has the same structure as R1, but I can't get there in a smooth way. So let's take a look at our options on the left. Again, this kind of creased version isn't an option right now because it wasn't differentiable to start with. This right here, this circle just has a fundamental different form than our real number line, essentially because it's closed. This closure right here makes it just a completely different shape. So it isn't homeomorphic and also not diffeomorphic. So we can't consider this to try to find an object that is this kind of similar, but not that kind of similar. Okay, Both of these generally have the same shape as a number line. This one, honestly, just is exactly the same. It is a line. And then I'm noticing with this kind of squiggle right here, I'm imagining it as maybe just like wet spaghetti. We could just hold it from the top and it'll just kind of fall into a straight line. And I'm not including any creases or harsh edges in there. Basically, we can very smoothly change a squiggle back into a straight line. And so that smooth transition, this diffeomorphism, shows, at least kind of conceptually, that a squiggle is diffeomorphic to R1. Now we can do something similar with R2. We could imagine, what are some like 2D surfaces that we could test out? We talked about that sphere. We talked about just planes. Maybe I could think about like the surface of a cube. That surface is two-dimensional. And maybe I could get like a wobbly plane out of this. So I could, here's my plane that just looks pretty normal, just normal grid lines. And then how about let me get some kind of warped plane, something like this. And now we can try to see if we can find any manifolds that are homeomorphic but not diffeomorphic to R2 or R squared. Here we're basically asking, can we find some things that have fundamentally the same structure as the plane, but we can't get back there in a smooth way? So the sphere and the cube we can kind of rule out immediately because they just aren't homeomorphic. They don't have that same fundamental shape because they are both closed. Also, I'm pretty sure this wouldn't count as a differentiable manifold just because we have all these edges. And then, so this right here essentially is just a plane. This does have the same structure as R squared. And maybe you can imagine for this bottom example, we could pretty smoothly just tug on it on both sides and kind of bring it back out to a standard kind of grid like this. And so I really can't think of any two-dimensional shape that is smooth already that can't smoothly get back to a plane. Maybe you could imagine a blanket, right? Like we could even, if we wanted to, kind of twist this top end of the blanket around so it's a little bit wrinkled in the middle. But we can always just twist the blanket back to a plane again. And as long as we're not creating just strict edges in our blanket, we can casually, smoothly unfold it right back to a plane. Again, not a proof, but just kind of a conceptual example of what's happening in that second dimension. Here's where it gets hard for me. I can't really picture what's going on in the third dimension. Here we have to somehow envision 3D space being warped, but apparently in 3 dimensions, it's pretty simple to warp them back into kind of standard 3-dimensional Cartesian space, just with like, normal grid lines. The issue, apparently, with the 4th dimension is that we get just enough leeway where we can create these smooth structures, again, that begin as differentiable, and somehow there's just enough wiggle room, but not enough wiggle room, where they start out smooth and they have the same overall structure as just 4-dimensional space, but somehow we can't transition between the two in smooth ways, between like our standard 4-dimensional space and this kind of weird, the math word is exotic, 4-dimensional space. So I have no pictures for them. I don't know what they really are like, but there are things called exotic R4s that have that same fundamental structure of normal 4-dimensional space, but then there is going to be no smooth mapping to go between the two. And this is basically the proof. Again, I don't know how to go into it formally, but that's the idea, that there exist these 4-dimensional structures that begin smooth or begin differentiable that we just can't get back to normal 4-dimensional space without causing a crease somewhere. And then the idea with higher dimensions, like the 5th dimension and onwards, is that we have too much leeway, or more than enough leeway rather, so that once we do have, say we're starting out with like a weird 5-dimensional structure, weird again, like weird in 2 dimensions would mean kind of warped, right? So maybe we have some warped 5-dimensional structure However, we do have enough leeway to kind of unfold and untwist this weird 5-dimensional shape to go back to the normal 5-dimensional space without causing any creases or edges. I think that's all I got today. I don't really have much more to share, and definitely do your own research if you're curious. So that's about it. Hope you enjoyed, and I'll see you tomorrow, and we'll get back to normal programming and actually solving some problems. Alrighty, bye for now.